Hello, in the third video in the series, we'll be discussing equilibrium, thermochem, and electrochem.
Our next topic is equilibrium, and so for dynamic equilibrium, where the arrows go both ways, we can say that K is equal to K of the forward reaction over K of the reverse reaction. So in this case, that would be in the numerator D raised to the D times the concentration of E raised to the E over A raised to the A times B raised to the B. But there are two different Ks, a K for concentration and K for pressure. And so next is equation relating these two. So Kp is equal to Kc times RT raised to the delta N. So R is 0.08206 atm liters per mole Kelvin, temperature is in Kelvin, and delta N refers to the final minus initial moles. Next, we'll discuss what happens to K when we manipulate the reaction. So, taking this one right here, A plus B goes to C with K. If we were to flip this to C goes to A plus B, that would be K raised to the negative 1. And if we were to multiply this by 2, so 2C goes to 2A plus 2B, we would raise K to the negative 1 to the second power. And similarly, when we add two reactions like 2A plus B goes to C plus D and D plus Q goes to Z, we cancel out the intermediates to get 2A plus D plus Q goes to C plus Z, and we multiply the K's. So I'm just going to rewrite the expression for K, and then we have Q, which is basically the same as K, except it's the initial values. And one reason why these two values are important is because we can use them to determine the net direction of the reaction. So for example, if Q is less than K, the reaction shifts to the product side, whereas if Q is greater than K, the reaction shifts to the left, creating reactants. And so if Q equals K, that means that it's at equilibrium. Next, we're going to set up ICE, or initial change in equilibrium. So we're given that for the reaction H2 plus I2 goes to 2HI, that the K is 51, and that the initial values are 1.22, 0.86, and 0.82. So from there, our next step is to determine Q in order to see which way the reaction goes. And so in this case, that would be HI squared over H2 times I, and that gives us 0.64, and Q is less than K, so the reaction shifts towards the products. So then we can use a variable x for our unknown. So since it's going towards the products, we're going to subtract by x on the left side, and on the right side, because the coefficient is 2, we're going to add 2x. And so for equilibrium, we bring this all together into one expression, and so it's 1.22 minus x, 0.86 minus x, and 0.82 plus 2x. And from there we can set up K, which we know, so 51 is equal to 0.82 plus 2x squared over 1.22 minus x times 0.86 minus x. And so from there we can calculate x to equal 0.68. And we can then find the equilibrium values since we know for x. So that would be 0.54 molars for H2, 0.18 molars for I2, and 2.18 molars for HI. And there are three different Ks within Kc. So that's Ksp, which is a solubility product constant, so from a solid to aqueous ions, Ka, which is an acid plus water, and Kb for base plus water. And for Ka and Kb, if they're given, we assume that they're weak acid or base, since if they were strong, they'd react nearly 100%. The next problem we'll go through involves Ksp. So for the solid, Ca3PO42 goes to 3Ca plus 2 and 2PO4 minus 3. We're given that Ksp is 2.0 times 10 to the negative 29, and we're asked for the final equilibrium concentrations of the ions. So ice doesn't apply for solids or liquids, and so we can just draw lines through those. And we start off with 0 for each of the ions. So then we know that the reaction has to be going towards the products, and so we add 3x and 2x. So we know that KSP equals 2.0 times 10 to the negative 29 is equal to 3x cubed times 2x squared. So we can calculate x, which must be 7.1 times 10 to the negative 7, making Ca plus 2 equal to 21 times 10 to the negative 7 molar, and PO4 minus 3 equal to 14 times 10 to the negative 7 molar. Next is Le Chatelier's principle, which addresses the question of if something is at equilibrium and changes, which direction will the reaction go to get back to equilibrium? So if we take this reaction right here, 2A gaseous plus B solid goes to 2D gaseous plus 3E gaseous. If A is added, the equilibrium must shift to the right. And if B is added, the equilibrium won't change, since solids and liquids don't affect equilibrium. And if D is removed, similarly, the reaction will shift to the right. And if we decrease the volume, that also means increasing the pressure. So that means the reaction will shift to the sides with fewer moles. So in this case, that's to the left. And so if the same number of gaseous moles are on both sides, the pressure won't affect equilibrium. And similarly, if we increase the volume or decrease the pressure, the reaction will shift to the side with more moles, so in this case, that's the right. Then, if delta H is positive, or the reaction enthalpy is positive, meaning it's endothermic, an increase in temperature means an increase in K, and so the reaction will shift to the right, but a decrease in temperature means less in K and shifting to the left. So if delta H is negative, or it's exothermic, increased temperature means decreased K and we shift to the left, while decreased temperature means increased K and shift to the right. Next, we're going to go through some definitions of acids and bases. So Arrhenius said that acids donate hydrogen ions and bases donate hydroxide ions, but this isn't always true. And then we have Bronsted-Lowry, who said that acids donate hydrogen ions and bases accept them, which is true most of the time, but not always. And then there's Lewis, who said that bases donate electron pairs for bonding and acids accept electron pairs for bonding, which basically contains everything previously said. Next, we're going to talk about the autoionization of water. So H2O liquid plus H2O liquid goes to hydronium aqueous plus hydroxide aqueous. And we know that Kw for water is equal to the hydronium ion concentration times the hydroxide ion concentration, which is equal to 10 raised to the negative 14. So in pure water, the hydronium ion concentration is equal to that of hydroxide, and that's equal to 10 raised to the negative 7 molar. And next we can write out the relationship between pH, POH, hydronium ion, and hydroxide ion. So they're all interconnected, and H3O plus times OH minus is equal to 10 to the negative 14, and pH plus POH must equal to 14. So POH is equal to the negative log of OH minus, and so OH minus is equal to 10 raised to the negative POH. And same thing for H3O and pH. So pH is equal to the negative log of H3O plus, and H3O plus is equal to 10 raised to the negative pH. Next, we're going to go back to the ideas of Ka and Kb. So for Ka, we set up the reaction HA aqueous plus H2O liquid goes to H3O plus aqueous plus A minus aqueous, where A stands for the acid. And so we can write Kb as A minus aqueous plus H2O liquid goes to OH minus aqueous plus HA aqueous. So Ka is equal to H3O plus times A minus over HA, and Kb is equal to OH minus times HA over A minus. So we can take the product of Ka times Kb, and after some terms cancel out, we're left with H3O plus times OH minus is equal to 10 to the negative 14. And so the product of Ka and Kb of conjugates is 10 raised to the negative 14. And this is looking sort of like the autoionization of water, and so we can draw out a similar square with Ka, Kb, pKa, and pKb. So we can see that Ka times Kb is equal to 10 to the negative 14, and pKa plus pKb is equal to 14. pKb is equal to the negative log of Kb, and Kb is equal to 10 raised to the negative pKb. And pKa is equal to negative log of Ka, and Ka is equal to 10 raised to the negative pKa. But this relationship is only for conjugate pairs, like for example NH3 and NH4+. And lastly, we have the Henderson-Hasselbalch equation, which says that pH is equal to pKa plus log of the concentration of A minus over HA, although we could also use a ratio of the moles, since molar is equal to mole over volume. So for example, if we're given 25 milliliters of 1.22 molar NaOH and 37 milliliters of 1.5 molar HF, and HF Ka of 7.2 times 10 to the negative 4, we can recognize that NaOH is a strong base since it has the hydroxide, and so therefore the reaction will go 100%, especially since HF is a weak acid. Since it's not one of the strong acids, which are HCl, HBr, HI, H2SO4, HNO3, HClO4, and HClO3. So we can write out the reaction of OH aqueous plus HF aqueous goes to H2O liquid plus F minus aqueous. Since sodium is a spectator ion, and from there we can set up ice, so we can calculate this into moles. So there's 0.0305 moles of OH to begin with, and 0.0555 moles of HF, and we discount H2O since it's liquid, and there's 0 of F minus. And so from here we need to calculate the limiting reactant, and since they all have a coefficient of 1, we know that the limiting reactant must be OH since it has the smallest number. So then for the change, we subtract 0.0305 from the left-hand side and add it to the right. And so for the final, we're given that OH has 0, HF is 0.0250 moles, and F minus is 0.0305 moles. And so from there, we can use the Henderson-Hasselbalch equation, which is simpler. So we get the pH is equal to the negative log of 7.2 times 10 to the negative 4 plus log of the ratio of 0.0305 over 0.025, and that's equal to 3.23. The next topic is thermochem. So we're going to start off talking about entropy, which is designated by S, and this describes a state of disorder. So for example, going from liquid water to gaseous water is a state change with increased entropy since they are more spread out. And similarly, going from 2NH3 gaseous to 3H2 gaseous plus N2 gaseous is an increase in entropy since we're going from 2 moles of gas to 4, which is a decrease in order. Next is delta H, which is change in enthalpy, which is based in heat. And so if it's positive, that means an input is necessary into the reaction, and if it's negative, that means there's an output and it's excreted. And in terms of the values, the delta S of the reaction is equal to the sum of the S's for the products minus the sum of S for the reactants. And similarly, delta H of the reaction is the sum of the delta H's of the products minus the sum of the delta H's of the reactants. So for example, for the reaction 2C2H6 gaseous plus 7O2 gaseous goes to 4CO2 gaseous plus 6H2O gaseous, the delta S of the reaction would be 4 times the S of CO2 plus 6S of H2O minus the sum of 2S of C2H6 plus 7S of O2. Next is Gibbs free energy, which tells us the amount of energy that comes out of a reaction or how much energy is needed for the reaction, and its units are kilojoules per mole. And so, if it's positive, that means it's non-spontaneous since an input is required, and if it's negative, that means that it's a spontaneous reaction. So the equation is delta G is equal to delta H minus T in Kelvin times delta S. And based on this equation, we know that if delta H is positive and delta S is negative, that means delta G is always positive and non-spontaneous. And if delta H is negative, delta S is positive, then delta G is always spontaneous. And so it's like a combustion reaction, like the hydrocarbon combustion. But if they're both positive, that means that at low temperatures it's non-spontaneous and at high temperatures it's spontaneous, and so it's temperature dependent. And similarly, if both delta H and delta S are negative, at high temperatures it's non-spontaneous, and at low temperatures the reaction is spontaneous. Here I'm just rewriting the equation, and so these use standard states, and so we assume 25 degrees Celsius and 1 atmosphere or 1 molar. So if we're given delta H standard and delta S standard, we can just plug those values in and solve for delta G standard. But delta G can be non-standard as well, so for example, there could be a no temperature, and in which case we just plug in the new T and solve for the delta G standard for the new temperature. But there's also delta G non-standard with a new temperature, and that would equal to delta G standard of the new temperature plus RT ln Q, where R is 8.314 joules per mole Kelvin, and T is once again in Kelvin, and Q once again does not include L or S. And at equilibrium, delta G is equal to 0, and it's K instead of Q. And so we can rearrange this, so we can write delta G standard is equal to negative RT ln K, or K is equal to E raised to the negative delta G standard over RT. Next up is electrochem, but first you need to understand the redox reactions and some of the important properties. So for example, fluorine is always -1 with another element, and oxygen is usually -2 unless it's forced to be -1 when it's peroxide or superoxide. Hydrogen is +1 when in a molecular compound, to -1 when in an ionic compound. Halogens are generally -1 unless forced to be positive by oxygen or other stronger halogens. Elements in an ionic compounds have an oxidation number equal to their charge. Elements that are alone have an oxidation number equal to their charge. Atoms in diatomic molecules have oxidation numbers of 0, and the sum of all oxidation numbers in a compound is equal to the charge of that compound. First is balancing reactions. So we're first going to break this up ionically. So that's H plus Cl minus plus K plus MnO4 minus plus H2O2 goes to Mn plus 2 2Cl minus plus H2O plus O2 plus K plus. And we're going to take out the spectator ions, which are K plus and Cl minus. So we're left with H plus MnO4 minus plus H2O2 goes to Mn plus 2 plus H2O plus O2. And from here, we're going to remove anything that exists in an aqueous solution, like H plus and H2O. And from there, we are left with MnO4 minus plus H2O2 goes to Mn plus 2 plus O2. And the second step is to think about what's oxidized and what's reduced, and we can use oxidation and reduction numbers for that. And so we find that oxygen is oxidized since it goes from -2 in MnO4 minus and -1 in H2O2 to 0 in diatomic oxygen. And on the other hand, Mn is reduced from +7 in MnO4 minus to +2 in Mn plus 2. We can first work on the reduction reaction, so MnO4 minus goes to Mn plus 2, and we can go ahead and add in H2O to balance O, H plus to balance H, and electrons to balance charge. And so if we do that, we are left with 5 electrons plus 8 H plus MnO4 minus goes to Mn plus 2 plus 4 H2O. And we can do the same thing for the oxidation reaction. And so that leaves us with H2O2 goes to O2 plus 2H plus 2 electrons. And then we can balance each of these half reactions. So we multiply the reduction one by 2 and multiply the oxidation by 5. And this is so that we can balance the number of electrons on both sides. So lastly, we're left with 5H2O2 plus 6H plus 2 MnO4 minus goes to 2Mn plus 2 plus 8H2O plus 5O2. And in order to balance this in a basic environment, we can add the same number of OH minus to both sides as H plus. And so in this case, we'd add 6 to both sides, and that would leave us with 5H2O2 plus 2MnO4 minus goes to 2Mn plus 2 plus 2H2O plus 5O2 plus 6OH minus. And next we're going to talk about electrochemical cells. So I'm drawing out this cell where H2O2 goes to oxygen on the left, and on the right MnO4 minus goes to Mn plus 2. And we want to track the flow of electrons, and so it's important to know which one's the anode and cathode, and the anode is oxidized and the cathode is reduced. And another important part of this is the salt bridge in order to keep the process going. And the next equation is delta G standard is equal to negative NFE standard, where N is the number of moles of electrons, F is Faraday's number, and E standard is the voltage. We're given the reduction potential for copper, so we can set this up. And we can draw on the salt bridge and the known concentrations of copper on each side. Now we can write out the reduction and oxidation potentials and sum that, and so we can get Cu1 solid plus Cu2 plus 2 goes to Cu2 solid plus Cu1 plus 2, and the voltage is 0. So we know that Q must be equal to the concentration of Cu1 plus 2 over Cu2 plus 2, and that comes out to be 2 times 10 to the negative 6 molars. And from here we can use the Nernst equation, which is E is equal to E standard minus RT over NF ln Q. And so E must be equal to 0 minus 8.314 times 298 over 2 times 96,485 ln of 2 times 10 to the negative 6, which is equal to 0.168 volts. And lastly, there's electroplating, where power sources are used to run reactions that are non-spontaneous. One example of this is gold plating a ring. For example, if we want to plate 3 grams of gold, and the current is 1.55 amps, and we need to find the time, we can arrange this so that we look at the units to make sure that we solve for this unknown. So for example, we start off with 1 second over 1.55 coulombs, since we know that an amp is coulombs over seconds. And then from there we can multiply by 96485 coulombs per moles electron to cancel out the coulombs, and 3 moles electrons over 1 mole of gold to cancel out the moles of electrons, and the molecular weight of gold we can divide by in order to cancel out the moles of gold, and lastly multiply by the grams to cancel that out, and so we're left with solely seconds, which is what we're looking for. And the final example is trying to find the mass given that the current is 2.10 amps and the time is 30 seconds. And so similarly, we're setting up the ratios and so that they all cancel and leave the unit grams, which turns out to be 0.043.
Thank you for listening.